All right, thank you for coming to our second meeting on the road, and actually we're in a different country now, and it's good to cross borders and cross the Atlantic on the other side of the pond and get over here and present a very fascinating and I think fantastic historical business opportunity, and also a little bit of technology and theory and science milestone for mankind as well. So I'd love to relate this to you and present. So I appreciate you joining us today. I'm going to go over the introduction to the company and then talk about the sun cell generator, some of the background about the process, and some of the timeline, and which puts it in perspective and gives you some insight into what it took to get here, and then how fast this thing is rapidly moving towards commercialization. So some of the heavy lifting is done, and now we're doing engineering, and it's actually a race to getting a product. And I know we can't make it go any too soon, that's for sure. So we're urgently moving that on, and we understand that there's a tremendous demand for this, and we're working to deliver on those expectations. So to give you an idea of what we do, this is a reinvention of electricity. There's a lot of things being reinvented, in a lot of different spaces in terms of telecommunications and communications, media and the like, and it's about time that electricity got a revision after about 100 years of being around. I guess it goes even back to the days of Volta, which is ancient compared to how rapidly technologies are proliferating now. So this is independent of the grid. So the traditional model of having a massive 10-acre central generation distribution system going out for many, many miles and covering an entire geographical sector or even entire countries is going to be replaced by autonomous individual units that are mass produced and extremely cheap. And then the days of belching CO2 and coal and all kinds of noxious toxins into the environment are gone. So it's based on classical physics that's been around for hundreds of years. And it was actually predicted that classical physics would work on the level of the atom, but suffice to say, no one up until now has ever solved that, albeit it can be solved. It's sort of, you read the textbooks, they say classical physics can't apply at the atomic level, you can't solve it. It wasn't solved, but it's absolutely provable that you can solve it, because it solves everything from subatomic particle masses to cosmological parameters, analytical expression, simple math, and easy to comprehend. And I'll talk about the alternative, which is really quite strange, the theory we're using today. It's based purely on mathematics. So it's very, very substantiated in hard physics and in massive amounts of validation and analytical, and I think it's substantially proven. I mean, you never prove anything in science, but the odds that's wrong, that we're making a mistake here, is very, very small. As you examine our materials, our publications, I think you'll come to the same conclusion. So we had to make a business model that would be competitive with the utility model, and we've done that as well. So we're reinventing electricity. We're reinventing the way electricity is generated. Of course, the primary power source is different. The equipment, it doesn't use turbines, doesn't use generators. It's entirely different. I'll go into details. And the business model is different as well. So this would be a model whereby we would outsource the construction of equipment, manufacture of equipment. We'd outsource the supply chain management, the installations. We'd have depot repair centers, all outsourced, and the repair thereof of the equipment. And we would just lease power sources. So you would pay, for example, a per diem rate with no metering. So again, it's different. It would be different than having transmission wires and then an electrical meter where the power is being delivered from a huge central gen power plant. And for example, rather using 100 carloads of coal per day at 100 tons per carload, we use water as a source of fuel. And specifically, we're using the hydrogen from the water molecule to form a new state of hydrogen. So that has profound implications for affordable, clean, cheap, readily, ubiquitously available power, not only in industrialized countries, but it can electrify other regions of the world that currently have a lack of access to electricity. And these are not a few people, but this is like a billion people without electricity. So the system is shown here on the left. It just very generally, it has an electromagnetic pump that injects molten silver metal. As you know, silver is extremely, extremely safe and non-reactive. And it has a source of hydrogen and a source of catalyst to take the energy from the hydrogen atom in a special manner, radiationless manner. I'll explain more about the process later. And it causes the hydrogen atom's electron to transition to a lower chemical energy state, which is predicted by physical laws. And we observe that by multiple techniques. And it makes enormous amount of power in the short wavelength spectrum, not X-ray, but higher energy than visible light. And then we convert that light, because it's higher energy than conventional photovoltaics can convert. We convert that light into a black body radiation by heating up this black spherical dome. And then it heats up like a giant light bulb and illuminates concentrator variety photovoltaic cells, which operate at more than 1,000 times sun concentration to produce electricity. So typically we would make the same output as a large solar farm. So it'd be like 150 kW and up, and we can gang these cells up to pretty much arbitrary scale. It would be DC, and then we can convert it into AC using conventional inverters that are identically the same as those that are used in solar farms. So the voltage can be that of a traditional inverter, like 380, 760. It's very compact. It can be about the size of a small refrigerator, like a personal refrigerator. It would operate at thousands of times sun concentration. The black body radiator for our application will operate somewhere between 5 and 10 million watts per square meter. That's insane power density. I mean, that's incredibly high power density. The reaction can achieve easily 1 million watts in a teacup. Like, there's no primary energy source that makes that high a power density. So this could be very, very compact. And it's permissive of making what they call thermal photovoltaic, which is not a preferred term of art because it's got a bad reputation, because there's nothing, not because the technology isn't great, it's phenomenal technology, it's just there's never been a primary power source that could heat a black body radiator up to 3,000 to 3,500 Kelvin and make that kind of power density. Millions of watts per square meter. Once you get up to that temperature, then you're emitting white light, which is very, very favorable for being converted into electricity using conventional photovoltaic materials at very, very high efficiency and very, very low cost, like incredibly low cost. Because it's so compact, you use so little material. To be very lightweight and compact, that it can go into motive applications, and where size matters. It could go into aviation, as well as cars and freight and rail and truck and marine. So it's pretty much applicable to all applications. So I was saying it's based on a proprietary systems, methods, reactions, catalysts, controls, parameters, many aspects of intellectual property, massive amounts of IP filed. And the product is what we call hydrino. It's a more stable form of hydrogen. And it is, as I'll show, ubiquitous. It's not something that that doesn't exist in nature. In fact, it makes up most of nature. It is the identity of dark matter of the universe. And not unusual that it was missed. Helium was discovered like 100 years ago by Lochner, by looking at lines in the sun, and then it was discovered through alpha decay, and it was mocked, scoffed at, and then ultimately identified as a new element. Fullerene, then there's graphene, and graphite and diamond, new allotropes, graphene and fullerene, for example. Two relatively new, like in the last 10 years, discovered allotropes of carbon, predicted not even exist. So you can look at hydrino as an allotrope. It's a different form of hydrogen. It's a different physical, chemical form of hydrogen. It's not a new element. It's not nuclear. It's just a stable state of hydrogen that it releases energy. Incidentally, you can make metallic hydrogen as well. You can compress it, and it will release energy transitioning back into regular hydrogen. Enormous amount. So this is a more stable form of hydrogen, but it doesn't spontaneously transition back into hydrogen, nor ordinary hydrogen. You have to basically tear the electrons off by high energy collision. You get electrons and protons. They can recombine back into hydrogen, but ordinarily it'd be stable under any conditions, any physical conditions. So it involves, as I was saying, water, fuel, and has silver as one of the components to provide appropriate conditions for the reaction to propagate. So it's incredibly safe, and the byproduct is this more stable form of hydrogen. It does not burn, does not react with anything. It's lighter than air, and vents to space. So it's about as safe as you can possibly imagine as any power source. It's hot, but it's hot like a light bulb. And as you know, if you turn a light bulb on and off, it's essentially instantaneous because it's releasing energy as light. And light is very effective at transporting power and thereby taking that power away from the reactor if you wanted to cease making power for any reason. Capital cost is extremely low. It's about 10%, maybe even less, than conventional capital equipment. And we're putting as a model for our commercialization of selling power for 5 cents a kilowatt hour on site, 24/7. But you'll see the cost of generation is phenomenally low. Because some areas of the world, maybe where they have oil on site or mine mount coal or hydro, it may get this low, but that's pretty much the cost of transmission and distribution of power. So if there's anything other than on-site power, it's very, very hard to compete with that. So that's kind of, and we did a model of all other competing power sources, all primary central gen sources. This is this is lower, undercuts those rates. So they're saying the only consumable is minimal amount of water you can pull out of the atmosphere. There's always water in the atmosphere, and you take a cold object and it'll condense, you'll get beads of water on it, so it's always there, even in the desert. So you always have a source of water no matter where you are on the planet. And this is, as I was saying, it's applicable to essentially all markets. We're going to introduce this in the stationary market, and then ultimately move into motive power markets, looking at large power users that use a lot of kilowatt hours, and then moving down the chain into the smaller markets in terms of their capital usage as we develop the technology and the business. So we're looking to do field trials in 2017 and do commercial units in 2018. And Dominic's going to go over the timeline. Dominic Jones, who's head of our business development, will come and talk after me. And He's a Brit, by the way, so you should give him a lot of leeway if he makes any mistakes. Sorry, just kidding. He's a great guy. He's tremendously proficient in what he does. We're lucky to have him. So anyhow, the cost or the amount of revenue that a generator typically generates based on typical cost in the U.S. is about $1 per watt. So if you have a 1 billion watt power station, it generates about $1 billion a year. And that just gives you an idea of revenue displacement or comparator of our power source. Capital cost, $50 a kilowatt, tremendously cheap. 20-year lifespan, that's based on the photovoltaic lifetime. It's pretty much warranted for that period of time. So you got an annual capital cost about $3 a kilowatt, which is basically the entire cost. There's no fuel cost. The operation maintenance cost is projected about 2% of cap cost, which is based on the experience with solar. And that translates in, or corresponds to a generation cost of about a millibuck per kilowatt hour, about 1/10 of a cent. And actually the number is lower than that, but that's so insanely low that I had to put something out there reasonable.
Millibuck per kilowatt. I never heard that before.
Yeah, millibuck per kilowatt hour. So a buck in the U.S. is $1.
Yeah, I know.
We call it a buck.
But a millibuck
Greenback.
is a new expression.
Yeah, smiling Washington, that kind of thing. So okay, I'm just going to go a little bit over the timeline. So that's basically the what the technology entails. To get there was a lot of work, and basically it's like starting with a white sheet of paper. There's absolutely nothing there, and I didn't start with H psi equals E psi, the I think infamous, but some people would argue famous Schrodinger equation, because I'd say, well, where can you buy psi? What is psi? And well, you can't get it at Walmart, you can't get it from Alibaba, you can't get it from eBay. It's just a figment of imagination. It's a mathematical construct where you take a bunch of derivatives and you get a number. And then you got to interpret that in terms of the physical world, and you can't. I don't care how hard you try, you cannot interpret that in terms of the physical world. So you really can't predict what hydrogen atoms can do if you can't understand what a hydrogen atom is. Like, what is an electron according to quantum mechanics? Singularity everywhere at once? I mean, what does that mean? Well, each one of those singularities everywhere at once is a different universe simultaneously. And then they're all entangled with each other, but none of the universes interact with each other. We only observe one universe. But we all observe the same universe, out of the infinite possibilities. But you could take some very exotic experiment and measure one thing in Paris and in some other place in France 50 miles away and instantaneously have effect. Well, why aren't all the infinite universes with the infinite number of particles interacting with each other and doing the same thing? It doesn't make any sense at all. No matter, or it means that all you can know is what the instrument tells you, and you're entangled with the instrument, whatever that means. And it says you don't know anything about reality. You can never. It says you can never understand reality or even perceive. It doesn't exist. And then you're just observing manifestations of math. That's another interpretation. Not very constructive if you're trying to engineer something. So, physical law has been around for a long time, hundreds of years, and they work perfectly well. And they work at the level of the atom too. And there isn't any in-between physics between the macro world where the physical laws work and the micro world. It's the same exact thing. So it just takes a lot of work to solve that and work all that out, and then to engineer something from that basis. So there's this intervening time, and then there was a breakthrough I'll talk about, and now we're moving to a product at enormously rapid pace. So everybody had a very, very adverse reaction to saying that physical laws work at the atomic scale. They did not like that idea, to say the least. And no one wanted to help us. I mean, in fact, they put up roadblocks every chance they could. And we had to fight through those. And we've had all kinds of attacks, I mean, literally attacks on that people were organized and activists trying to put brilliant light out. Which was unfortunate. It took longer, but we did work through it because the science and technology are very sound. and we were successful. So now, in today's era, they're saying what I've been saying all along, that either you can't know anything about reality, or there's all these realities that are occurring simultaneously, and somehow we only observe one of these realities, of the infinite possibilities. So quantum now has to address what exactly is an electron, what does it look like, and how does their theory apply to the real physical world? Because it's actually the point now where you can actually image electrons. You can image molecules at the atomic scale. So you can actually see they're real. You can do things like migration of electrons, free electrons in superfluid helium. You can see that they're real by their migration behavior. There's ways you can interrogate atomic particles now that show that they're real. So you really need to have a physical theory. So they're trying to reinvent quantum to address that, and it turns out it's already done. Everything from subatomic particle masses to cosmology, 1 followed by 85 zeros of scale, is already solved, and it's absolutely perfect fidelity of predicting the physical world. And it predicts this new power source, which is the reason why theory exists, so you can create, invent, and control nature to do new things. So the other problem, and not to beat a dead horse, that's expression US. You probably have something different here. I heard in the Netherlands they said that you're healthy as a chicken. And I said, well, healthy chickens get eaten, so it's not the greatest. Something like that. So we have different expressions. But yeah, but there is a consequence of having a wrong theory. And the consequence has been that society is stagnated and we have very low economic growth. So back when we were using physical laws and we were inventing electricity and we were inventing the internal combustion engine and we were inventing aviation based on physics, the economy exploded. And we had incredible growth. There was incredible growth and prosperity, and then it dropped off the cliff. And as much as you talk about social media and things like that, it really doesn't add that much to productivity the way these giant inventions did. So I would argue that the sun cell is a giant invention. It basically reinvents electricity, it'll reinvent aviation, it'll reinvent and replace the internal combustion engine. So it does all three of the prior giant inventions. So I'm saying you're looking at a monumental economic opportunity. So where did the theory, why was I interested in the theory? Well, I took quantum mechanics and I just couldn't believe that there's this kind of fantasy world where you just sort of math and it's really kludge. You just kind of pick things and curve it. Like the standard model, everybody says it's so great, it's absolutely perfect. It's got 26 adjustable parameters. It's not a theory, it's just a list of stuff with parameters that go from one thing to another with just things you make up to fit the data. So it's not really that satisfying in terms of physically understanding. Whereby the approach I'm taking, classical laws, predicts all the leptons, quarks, bosons, all of them. It predicts it from fundamental physical laws. The same laws predict acceleration and expansion of the cosmos, the ionization of atoms, the bond energies of molecules, and so on. It's the same exact laws. Very simple set of laws. Mechanics, electromagnetism, allow you to predict everything that goes on all scales of the universe without any parameters other than the measured fundamental constants of nature, like the properties of space and time. So I wasn't really satisfied with it, and then one of my professors gave me a paper he later published in American Journal of Physics about looking at why accelerating charges radiate. So remember, the electron and atom keeps going around in orbit, otherwise it'll be changing. It has to go in a periodic orbit. It has angular momentum measured. So it's constantly accelerating because it's constantly changing its direction. It's like a skater, you go straight on ice, but you have to have a force to turn. Well, it's constantly turning in a circle. Or any kind of pattern. It's got to be constant turning because it's not moving off to infinity. It's still bound to the proton. So therefore it's accelerating. And he gave me this paper explaining why accelerating charges radiate. And I said, well, why isn't it radiating the atom? Because that's a fundamental thing that you learn, the fundamental phenomena, or the question physical laws in quantum mechanics, is they say the atom is constantly undergoing acceleration and it's not radiating. So their answer is, it doesn't obey physical laws. Like, maybe you haven't solved what it is correctly, and it would obey physical laws, because they presume it's like the moon going around the Earth. It's a nice model. You can see it every day, and the Earth going around the sun. It kind of makes some sense, planetary model, going back to the ancients, like the Greeks, and they'll say, oh, okay, the electron's bound to the protons, so maybe it's like the moon. Well, maybe it's not, and it turns out it isn't. And if you solve what the electron really is, it obeys physical laws absolutely perfectly. So, and then the other thing is that electrons in synchrotron radiation, free electron lasers, and plasma obey physical laws. So why is it when the electron is bound, it goes out of the free electron laser and gets bound to a proton, now all of a sudden it's pure math, there's infinite number of universes in parallel, or you can't know anything about reality? It doesn't make sense. So maybe it's not solved right. Go back, solve what the electron really is. So you can there are laws of what photons are. Everybody knows those from power transmission, lasers, and all kinds of optics. And it's really quite simple. You just take the equation for a photon, and there has to be something, the source of it, and you know antennas transmit power and they emit like radio waves. So you have an antenna, emits a radio wave. So you know what the equation of a radio wave is. Why don't you solve what the source had to be for an individual packet of what makes up a radio wave? And when you do, you get the structured electron. So it's a source and sink or absorber, like antenna is a source and sink. It can transmit and receive. So you take the individual packet and say, rather than a whole bunch of photons making up a wave, why don't I just take one, match it to the source of that wave is, and I'll solve its structure. So treat the electron as a source current, and you can therefrom predict physical phenomena like on atoms, and it matches everything perfectly. So it's got a certain current pattern. It's like a soap bubble when it's bound. It's two-dimensional. So there's a discontinuity in charge and current to give rise to discontinuity in field. These are all absolute predicted solutions of Maxwell's equations, Maxwell electrodynamics, classical physical laws. And it matches everything measured on the electron: Lamb shift, fine structure, hyperfine structure, G factor, selection rules, transition, lifetimes of states, etc. Analytical expressions. Fundamental constants only. Perfectly physical, intuitive, and you can make computer graphical models of what it is physically. So in quantum, this is one electron. These are different patterns that represent one electron. Now remember, the electron is supposed to be a single point. So now here's the contradiction. Obviously it takes up three-dimensional space, and they're saying that's a single singularity with no volume. So they're saying, well, that actually is the electron everywhere at once. And then you get into this whole thing. Well, how can it be everywhere at once, and what's that really mean? And so it's very, very esoteric. I won't spend a lot of time, because a lot of people spend a lot of time, and I think they go crazy just thinking about it. So the best thing to do is to say it's wrong and go solve what it really is physically. Trying to dwell over a bad idea and putting a square peg into a round hole. So it's like how many fairies can dance on a pinhead. I mean, it's just not the kind of problem you want to waste a lot of time on. So once you solve what an electron is, you can even solve analytically even things as complicated as DNA. Oh, and incidentally, every single electron, every atomic electron, every molecular, there's a molecular electrons involved in molecular bonds. This is exactly what they look like. This is down to the precision of the physical constants of nature for every single electron in that molecule. And the electron is not a singularity, and it's not everywhere at once. You can actually measure electrons in molecules. You can see There's hydrogen here. These are carbon in these rings. And this is the analytical expression. You can see it's a very, very exacting overlay to the limit you can measure this. And the bond energies and the energies and every aspect of this analytical solution matches the known parameters of pentacene, for example. And you can do that for boundless molecules of boundless extent and complexity. So we compared this. We did a comparison of quantum mechanics, you can see here, and this classical approach. So basically, molecules are like, they're made up of bonds, and each bond can be thought of as a brick. Like you take a building and it looks really complicated, it's a lot of bricks, and you're just putting bricks together. So you can solve the carbon-carbon bond, the carbon-nitrogen, carbon-oxygen, you know, the amide bond, the nitrile bond, you can, all kinds of stuff. The individual building blocks. So we took here, I took 415 building blocks, and I said, well, let me solve whatever's available that quantum can solve, I'll solve it. And it matches to a part per 100,000. Limits you can measure it. And then do the same thing with quantum, and you can see it's just completely random. This is their solutions versus the same molecules solved with these building blocks. So all it's doing is just taking solutions for building blocks and adding them together to boundless extent and complexity, and it matches the limit you can measure it for everything that's test part. We have a molecular modeling software, Milzian. It's available on our website. We have about 5,000 users. They say it's about 100 years ahead of anything they've ever seen. It's absolutely exact. So it becomes quite intuitive and very understandable once you have a physical model. And here's some other solutions of molecules, what they absolutely look like. And you can drill down and get the dimensions, the charge distribution, the kinetic energy, the potential energy, the magnetic energy between the electrons, every single point on this surface that comprises the current density or the current of the electron for all these incredibly complicated models. So I think this will lead to explosion in technology as well, having the exact solutions for physical matter. And you can do condensed matter as well. Same equations. So on that timeline, even to this day, we're criticized that there's no publications. There's no peer-reviewed publication. Yet, we have 100 peer-reviewed publications. And this was even a featured publication in European Journal of Physics D, which is a very prominent journal here in Europe. So there's many, many publications. You can see 100 to be exact. And we're adding to that. And we've had massive validations over the years. So we've always been very transparent, very open on the theory. The theory has always been publicly available to let anyone in the world comment on it. We have an open public forum that critics can publicly comment on. So, so we've always been open to peer review. So if you see something that says that we're not publicly releasing information, it's not true. So once you have a physical theory, what can you do with it? Well, theories are worthless, except, I mean, they're interesting. You can write books about it, and you can teach classes and give lectures. But really, the whole purpose of what mankind's endeavor has been, since he's looked at stars or pondered about fire or anything in the physical world, is how does it work, and how can I utilize it to improve my standard of living? One noble aspect for the utility of having a theory. So in this case, the same applies. And we can do something really, really very cool with it, and that is make a new source of power that's clean, cheap, will save the planet from CO2. Even if you don't believe in CO2, eventually if it goes to infinity, it's going to be a bad situation for the planet. Even if it's not having a problem now, eventually it will if it keeps accumulating. And acidify the ocean and who knows what. So suffice to say, we don't have to worry about that anymore because we have a power source that doesn't release any CO2 at all or any pollution whatsoever. So we'll talk about the invention of the hydrino. So that's where, along this timeline, there's inception of theory and then on to predicting the lower energy state of the hydrogen atom. So just in very graphical terms, cartoons actually, but it gets the concept across. So you have the blue guy, which is hydrogen atom. It's like a soap bubble with a proton in the middle, and there's an electric field between the two that holds the bubble bound, and there's motion on that surface. That's the current that gives rise to all the phenomena like electron spin and other properties of the hydrogen atom. The yellow guy is the energy acceptor. So typically the hydrogen atom has the electron go, the bigger bubble can get blow up until it ionizes off as a plane wave, as a free electron, and it releases that light and goes back to the state again. So everybody's familiar with that mission of hydrogen, but no one's really familiar with this, because this is predicted from the theory, that the hydrogen atom has a lot of energy available to give off, in addition to what it gives off when it forms an ordinary hydrogen atom from a proton and electron. But that energy can't come off as light. So for the one electron atom, there's a special case where you can transfer energy from the blue guy to the yellow guy, and the electron can drop to a lower energy state. And that's a radiationless resonant energy process. It's kind of like dipole-dipole coupling and other interactions that are known to man can cause or permit through space energy transfer without emitting light directly. Once that occurs, then you do get light emission because the electron's unstable once it transfers that initial packet of energy radiationlessly. The electron will accelerate greatly and form a smaller radius until it stops emitting light, and then it's stable indefinitely until you basically smash it with some high energy particle and ionize it back to its constituent particles. But for our purposes, it stays in that state. We're not going to revert it back to ordinary hydrogen. It drops down this hydrino state and stable. It doesn't react with anything, doesn't even emit or absorb light. So the energy transferred from the blue guy to the yellow guy is a huge amount of energy. So high that the resonant accepting reaction has to be an ionization reaction. Because even the most stable atom, helium, ionizes 24.59 electron volts, and the amount of energy is an integer of 27.2, which is the energy, potential energy of uncatalyzed atomic hydrogen. So it's big energy. It's got to be an ionization reaction. And I'll talk more about that, because this is one of the key steps, understanding that, to make the sun cell have these massive kinetics. So the kind of radiation, as I was saying, is unique. It's a continuum high energy light. And it turns out that continuum high energy light can ionize atoms. Particularly, they can ionize the atoms in the gaseous corona, the gas around the sun, and make the sun look like it's very, very hot. Like the sun looks like it's 2 million degrees if it's being ionized by thermal mechanism. But there's other things in the sun would say it's not thermal mechanism. For example, the surface of the sun is only 5,600 degrees Kelvin, whereas the gas around it looks like 2 million degrees Kelvin. The explanation for that, in addition to the explanation of why you get events like flares and active corona that can emit the entire power of the sun coming from that region, is that there's another energy process. It's very energetic, doesn't involve fusion. If it's fusion, it takes like 100 years for that fusion energy to diffuse through the sun. This is really instantaneous. There's something very powerful active in the corona and in flares. And it's a mystery, and still an unsolved mystery. But the explanation for that is that it's being ionized by this high energy light that's being emitted from this hydrino process. The hydrino process can be created also by atoms of hydrogen at very, very high density. They can interact with each other and do the very same thing as I showed in that prior schematic on the mechanism. In fact, you can see these spectral lines on white dwarf stars that match that radiation that we're seeing in the lab. Where they have no corona, there's no gas around white dwarfs to absorb the light because the gravity is so intense. And you can see exactly the same spectrum on the surface of those stars as we're seeing in our lab from our reaction. And that radiation is coming from all over the sky. The same radiation we're seeing in our labs coming from all over the universe. Astrophysicists don't know what the origin is. It turns out there's a parallel discussion in the astrophysical literature of what the nature of dark matter is. Dark matter makes up almost all the mass of the universe. It doesn't absorb or emit light. It's a real thing. This is the map of it. Ordinary matter and dark matter. This is another map throughout the entire cosmos of dark matter. It makes up about 100 times more mass than what you can see out there. Essentially, everything you can see is hydrogen. And what hydrino is, based on the recent data of the behavior of dark matter and this emission that matches emission from our lab, hydrino appears almost overwhelmingly to be the identity of dark matter. And even astrophysicists are saying that dark matter has to be some unusual form of hydrogen and that doesn't emit or absorb light. That's what we're forming in the lab. So you got fission, you got fusion, you got other kinds of indirect fusion, which is solar or hydro because rain fills up dams and like. It also uses gravity. So you got these primary energy sources. This is a new one where hydrogen goes to dark matter form of hydrogen. It's an entirely new form of power, entirely new process. And you can make the kinetics massive. Like even talk about fusion. Fusion in the sun has a power density of a compost heap. It's very, very low power density. And to get it to high power density, it's either extremely dangerous trying to confine it, and you got to use things like tritium because the rate is so low. It's vanishingly low rate. It's not the holy grail by any means. I think it's actually dangerous using tritium and extremely expensive, and it's not very, very high utility compared to this. This is every category. It's off the charts more favorable and doesn't involve anything radioactive at all. So, so that's your choice. I mean, you can go to fission, fusion, burning, or you can go to dark matter as a primary energy source in terms of the process. All right, so we'll look at the characteristics. So this is the spectrum. It goes down to 122 electron volts with a cutoff thereof. So it's really high energy. It's about more than 100. It's hundreds of times the energy of burning stuff. And it makes a product that's completely clean and lighter in the air and goes out of the atmosphere. So this is looking at a spectrum that we obtained in the lab. And this is a characteristic signature of the hydrino process. And that signature, as I said, is coming from all over the sky, and particularly dark matter forming regions. And you can see dark matter by this dark ring. And you can see there's nothing glowing here, whereas everything else glowing, including the stars, is basically hydrogen. So this stuff that's not glowing can be seen because it has a massive gravitational field. It's lensing galaxies from other parts of the universe. For example, here, it's you see all these galaxies are kind of odd-shaped. If you turn the telescope, something called a parallax, like the angle you're looking at it, and it'll move because it's not really there. It's being lensed. The light is being lensed because there's a huge gravitational field there. So dark matter and hydrino seem to be the same thing. So we have hydrogen atom, hydrogen going to dark matter form of hydrogen, and releasing enormous amounts of power and producing this kind of light, which is extremely, extremely high energy. The other unique thing is, I'll show you, there's essentially no visible or infrared light, which is a very, very unique signature. We've had a lot of experts look at it. No one even knows a light source will produce essentially all high energy light and no visible or no infrared, and it's continuum radiation. That's why it hasn't been observed. It's all frequencies, all wavelengths. To anybody looking out there, it'd be some background band. It wouldn't be discrete lines. Like here you'd see discrete lines here, and you can say these are oxygen ions. It's a broad band, and it's in an energy region where very, very few people even have the instruments. Like I'm only aware of us, and another lab here in the Netherlands that even has this equipment. It's pretty rare. that looks at that spectral region, because you can't even look at it with a window. You have to actually have a pinhole. There has to be a connection between the light and the instrument, and you have to do really heavy pumping to keep the pressure low in the detector to do that. So it's kind of an art and a unique instrument to even look at this spectral range, this energy range. So we have a lot of analytical techniques to identify this new form of hydrogen, and these are some of them. And we've been publishing on the identity of hydrino for quite a while. And as you go on our webpage, we have rotation, vibration, total energy ionization, many, many different techniques that we've done in terms of identifying that new state that are absolutely unequivocal. So given the process, we have to harness that. And over the years, we came up with a lot of different approaches. And unlike, I give the analogy of recombinatory chemistry in drug discovery. You can take chemicals and you just take a whole bunch of bottles of stuff and put them all together and throw that into a robot, and it goes and puts them on microtiter plates and does some kind of test. And you go through thousands and thousands and 10,000s, 100,000s of screens, and nothing shows up. And that's it. You lost your bet. It's like an oil well. You drill an oil well, you don't hit oil, that's it. So it's a zero. This is not a zero-sum game. Every single step was necessary to move forward to get to the sun cell. We had to build upon knowledge of the kinetics and the products of reaction, the analytical, the theory advancements, validations, etc., to get to the device. So this is a plasma device, and where we're looking for direct conversion, because plasma can also produce heat. If you're going to use a heat system called Rankine, which is making steam, you have to turn a turbine and then a generator. So you have to, there's inefficiencies involved. So you have to have a lot more heat than the electricity you ultimately get out. So if you're driving plasma with electricity, you got to get a big multiple of heat to make electricity from the heat, and therefore get a net gain. So this was a direct plasma to electric conversion approach, and we had some success with it. This is a plasma technology we did again. Again, it's electrically driven. You need to have a huge gain here. In every single device we got power. Every device we published on, we had power. We knew it had power very, very early on, but the power density was low and the gain was problematic, or regenerative systems that wouldn't degrade from the reaction at too fast a rate to make it economically viable. So there's a lot of impediments. We had to get something that's competitive with fire. It was 24/7, 365, capital cost was competitive with the internal combustion engine. It's like $50 a kilowatt. I mean, internal combustion engine is a very, very hard act to follow. So we went through a lot of different approaches, glow discharge, microwave cells with McCurl and Bienecker, and you know, there's a lot of approaches. RF cells, radio frequency, 13.56 megahertz. If you're in that business, you probably know what I'm talking about. So a lot of different things. So then there's another development beyond plasma, and actually that advanced to a point where we could actually have the plasma run on its own, and that was actually replicated over here in Europe by Dr. Johannes Conrads. Very, very interesting. Power density was low, but it would actually make plasma of hydrogen thermally, and you could even turn the thermal power off. As long as it's hot enough, that reaction would sustain for some very short period of time, but much longer than you'd expect by any kind of known physical mechanism. So it evolved eventually into a solid fuel. And the solid fuels were probably as close as we could get to something that could run a central turbine design plant. It was a chemical reaction to make the catalyst and atomic hydrogen. Got up to reasonable power densities. The problem was to regenerate the chemicals to make a complete cycle. And there's no chemical reaction that's always 100% efficient. So I got down to what is the capital cost of chemicals and how can you process those back into the original starting materials. And there's definitely some challenges. Albeit it definitely makes power, and it makes a reasonable power density compared to, say, coal-fired plant. Then we went to electrochemical to circumvent using central power station, to avoid going to a 10-acre plant, billion-dollar capital investment, multi-year trials before you build the next billion-dollar plant. And this actually worked very well. This is something where we put current in, we created atomic hydrogen, and the catalyst would be created by electrochemical process, created hydrogenos to drive the reaction, very, very high energy release. And we were showing by very astute experts, and these validations are on our webpage, that we're getting about 40 times more current out for current in. So we charge it for giving them current, it's same current, same voltage. We discharge it, and we get 40 times that. But the power density was low. And this reaction's super energetic. So we tried to scale it up to higher power. We had a lot of problems with corrosion, which all fuel cell guys, no matter what, they have those problems. But this is energetic chemistry. So that was a challenge with that approach. So then came the eureka moment. We have power, we have multiple systems, we have analytical, we have the theory from Quarks to Cosmos, I have the catalyst identified from that theory, that's the ultimate catalyst. And then what is it that's holding back the reaction? The real secret there is that as the hydrogen atom transfers energy to the catalyst or the energy acceptor by this radiationless step, this energy is big, so it ionizes the electrons that as the only possibility of a reaction that can accept that amount of energy. So you end up inherently with ionized particles. That is, you have positive and negative species produced. And that space charge, that is that charging up, prevents this occurring to the same reaction rate. So it's impediment. So the more you do it, the more charge buildup and the more impediment you have of further reaction. It's like if you walk across the carpet, you probably don't have that in England. We have it there back in Pennsylvania. It's very cold. You touch a filing cabinet and you get a shock. Well, if it kept building up, your arm would be like hitting lightning going through it, and it would be a stick of toast. So luckily that doesn't happen. It's because your energy level gets higher and higher, and then it basically repels more electrons going onto your arm. So in this case too, it changes the energy levels. So there's a way of actually using that to the advantage of making the reaction go to high kinetics. And that is, in a typical case, the more charge, the more energy. That is, like if you look at a toaster, for example, V equals IR, Ohm's law, that the more current, the more voltage it takes to drive that current through the toaster. And voltage is joules per coulomb. That's energy per charge. There's something called an arc plasma state that actually is the opposite. The higher the current, the lower the voltage. The lower the joules per coulomb or energy per charge. So you get like a positive feedback. So when we apply those conditions to reaction, boom, massive, explosive kinetics. Not percussion wave explosion, but light, just a blast of light. That's 5 million watts, and we've advanced this even further. We've advanced this about a factor of 5 over that in our lab. We are getting so much light, we can't even look at it with a spectrometer. We have the spectrometer on the other side of the room, and the slits are so closed, they're dialed all the way back to the laser can't even get light through them. And it's going off the charts. It's massive, massive power in a very, very short optical region. The spectrum looks like something no one's ever seen before. I haven't seen anyone that's come up with an explanation for this. That we get this extremely high energy continuum light, and there's no visible or infrared. There's some, you can see the light from that blast, but it's very, very small compared to the power. It's very, very short wavelength region. And we have a calibrated instrument that's state-of-the-art calibration of the short wavelength. So this is an absolute power measurement, and it's showing in this case, 5 million watt peak power and 1.3 million watt average power over the life of that state. That state lasts 1,000th of a second. And that's coming from a pellet that's only a few millimeters in diameter. So you can take millions of watts in a few millimeter diameter volume. There's nothing ever been that high power density short of like atomic weapon explosions. Enormous power density. And the other thing is, like if you look at this vent, so this is 1,000th of a second. So if you can make that happen 1,000 times a second, you've got continuous power at that density. And this is actually at the end here, it's actually making power. There's no electricity, there's no chemistry possible. It's just making power sustained. So it can become self-sustaining as well. And I'll show that feature, which is very, very fascinating, and it's important commercially. So then we got into inventing the sun cell. So now the idea is how do you fire that 1,000 times a second to get sustained power? So we looked at a lot of different engineering approaches. And you can see a lot of those engineering approaches and the discussion of those in our January 28th video. It's on our webpage. We looked at things where we were looking at powder injection, slurry pump, where you have the rollers and they're sucking up fuel that includes hydrated metal. So it's got to be extremely highly conductive in order to get this arc plasma state. And it has to have a source of H, well, water could be a source of H, and the catalyst, and water can also be a source of catalyst. We looked at pneumatic injection of powders. We looked at pelletization. So we have pneumatic injection of powder, we have a cyclone separator that would return those powders, make it a continuous cycles. Remember, we not only have to fire it, but we have to make it a closed system so we don't use up the chemicals. And it has to be pretty much 100% recovery. So we'd run into impediments we had with solid fuel technology. So this was a pretty interesting one. You can see this on our webpage. It turns out that we were firing pellets in that demonstration I showed. These were fuel pellets, little tiny several millimeter diameter pellets. So you can actually make those kind of metal fuel pellets at thousands per second by just dripping molten metal in the water. Then you'd have a mechanical system and a pneumatic injection system, and you could fire them into rolling electrodes and put pressure on, apply the current, get the high current that initiates this reaction by making this arc plasma state. It actually works really well. But again, there's impediments to that. So, and then there's electronic ignition system we developed with the Columbic Technologies up in Boston. So a lot of steps to get to this. This is molten metal injection, and it's got tungsten electrodes. That's a glove box. That's somewhere people put their hands in. And that's a big thing. And it basically vaporized the tungsten in seconds. And that whining sound is the alarm on that huge glove. It's a two-man glove box. And it overpressurized. It's such a huge thermal event. It overpressurized, set off the alarm. And you can hear that clicking. It's trying to adjust the pressure so the whole front doesn't blow off of it from the pressure. So it's incredible amount of power. It's off the charts power. So I mean, tungsten vaporizes like 12,000 Fahrenheit, and it just vaporizes. And you say, well, I could see it melting, and maybe it wasn't really tungsten. It's 99.9. The melting point is that high. The vaporization really is 12,000 Fahrenheit. And you say, well, how do you know it's vaporized? Because we could see tungsten ions in the spectrum. It's literally vaporizing it. Now that's great. It shows it has a power density like no one's seen before. And that was macro scale. If you just wanted to see how much power, all you have to do is put a spectrometer on that. That would have read 6,000 degrees centigrade. That's hotter than the surface of the sun. And then you can say, well, it's that big, and how much power is it? It's millions of watts. I mean, it's really easy to confirm. That is enormous. And how much power is going to? About the amount of 2 hair dryers. I mean, it doesn't take a rocket science to tell. You can't create that. We can't fake that. You can't take vaporized metal and all of a sudden it just boom into this incredibly hotter than the sun plasma. So, but it's a problem because it vaporized electrodes, and electrodes cost more than the power we got for those few seconds. So And this is what the cell looked like afterwards. I mean, it wasn't much of it, and there were big tungsten plate electrodes coming off these bus bars, and they're gone. So, and tungsten's kind of expensive, so you don't want to, that's not a good economic.
That's what I want to say. I had a couple of electron beam accelerators that I had built and run, and I believe you 100% that you have burned a lot of money to come between.
That's right, yeah, it's true.
Definitely.
Burned a lot of money.
I know the price of the tungsten electrodes.
And these were 1/4 inch thick too. They were heavy tungsten electrode, parallel plates. So, so we fixed that. So these are dual molten metal injectors. So these are tungsten riser tubes, carbon refractory material, and suffice to say we don't have that problem. And this is what the sun cell looks like. We would love to bring it over here, but you know, there's some issues about getting it here in time.
You said it's here inside. Yeah.
What's that?
You said it's inside the white case here. No.
No, we would like to bring it over. We'd like to bring it over, but we just had, we took it down to DC with us. We could take it down there, but it's kind of hard to bring over here. But nonetheless, you can always come over and visit at our facility. And this is 6 inches in diameter across here, and it's all tungsten. It's got graphite bolts, tungsten reservoirs. It's got a spacer here to electrically isolate these two. And then down the electromagnetic pump, we have a connection for positive and negative. So these are oppositely polarized. And when they pump, there's 2 streams of molten metal, and then they intersect inside here, and then it ignites when they oppositely polarized molten metal streams of silver touch. And then you get the high current, and that's your ignition current to start the process. So, so now on to the sun cell and how it works. So this is our commercial device. So it's basically a big light bulb. So it's 6 inch diameter, and let's say a light bulb, halogen light. So let's say a tungsten incandescent light. Think of that. Tungsten incandescent light has a filament, and it can get above 3,000 degrees Kelvin. So we're going to run this at 3,000 degrees Kelvin plus, 3,000 to 3,500 Kelvin. So, so if a light puts out 300 watts, we want to put out somewhere between 300,000 and 600,000. So it'd be 1,000 to 2,000 times more area, but it's basically the same exact problem as an incandescent light. So the light bulb then shines that light onto photovoltaics that are matched to the spectral emission of a black body. Black body just makes broadband light. I'll show you what it looks like. So black body spectrum looks like this. It's just basically all wavelengths. The hotter it is, the more it shifts to the shorter wavelengths. But if you have it at, say, 1,000, like where stainless steel melts, that curve would be way over here, and photovoltaic has to have light in this spectral region, like blue light to red light, in order for it to work. So it won't work with infrared light very well. So we want to shift it into a region where the photovoltaics work well. So that's how these are matched for this light source working at 3,000 to 3,500 Kelvin. So the device is comprised of electromagnetic pump, and that's basically permanent magnets and current that go in perpendicular to each other, and then the pumping is in the plane perpendicular to those 2 perpendicular axes. So it has no moving parts. That's the important thing. Just use permanent magnets and current to pump molten metal through these riser and ejector tubes, injects that metal stream into this chamber, and they're opposite polarity, and when the 2 streams meet, you get a high current, and you get the arc plasma state created, which drives a very high kinetics of this hydrino reaction. That short wavelength light is converted into black body radiation by illuminating this graphite or carbon sphere, and this is all closed, so the silver and everything is closed in here. The only thing going in and out is hydrogen that permeates through that black body sphere. The catalyst, and which is a very, very stable oxide, stays inside the sphere, and the silver stays inside the sphere. That's the conductor that allows the creation of the arc plasma state. And then there's other things like cooling technology. There's what they call cold plates. and they're micro-channel cooling design, and there's some other external cooling heat rejection that goes with this. There's some panels that cool the walls, and then there's the support electronics that provide the ignition current, the electromagnetic pump current, etc. There's some pumps and startup battery, radiator here for heat ejecting, this outside cooling capability. So as I was saying, you have very, very intense short wavelength light shown here. So you're seeing some of the light, but most of the light is in a region your eye can see. It's converted into black body emission of the appropriate spectral profile for photovoltaic conversion. So this is actually showing 3 layers of the photovoltaic cell. So these concentrator photovoltaics actually don't have a single layer. Like the ones that you see out in the solar farms, they're crystalline silicon. And they are only about 17%, 20% efficiency. These can be 42% efficiency in the field. That's kind of where they're at right now at concentrator, working at 1,000 suns versus 1 sun. So 1 sun is what you get just sitting something out in the backyard. If you take a big magnifying glass or a huge parabolic mirror, they use something that's like 30 feet across, 10 meters across. They concentrated with these mirrors into something the size of a wallet. And it's extremely intense light. I can burn through like quarter-inch steel like in under a minute. It's like a really, really intense. And they're much more efficient because the higher the concentration of light, the more intense the light, the more efficient they are. And they spent the extra money by making multiple layers because you're not using a whole field of solar panel, you're using a very, very small amount. So it affords to make multiple layers. So each one of these layers converts a different region of the spectrum of that emission from the sun, and similarly, we can do the same thing here. There's another advantage with our light source, is that light that bounces or that travels emitted from this surface goes to the PV on the inner surface. So it would go from this surface to the inner surface. Whatever is not converted by traveling through this blue layer, it bounces back to the light source again. So it can be reabsorbed. And there's something called emissivity. We're using carbon. Emissivity is 1. That means whatever bounces back, essentially 100% of it's reabsorbed, and then re-emitted at this characteristic spectrum, which is ideal for the photovoltaic we're using. So we theoretically get a lot more conversion efficiency because we can recycle the light. You can't do that with conventional solar, even of the concentrator variety. Oh, and incidentally, this is a commercial product made by Azure Space, which is a German company. They make the photovoltaic panels for satellites. And it comes with the cooling. So this is all turnkey commercial products. So we're pretty much making the light source, and then we're relying on concentrator photovoltaic manufacturers to make the converter of light to electricity. And there's a number of them. And we're using Massimo in Nashua, New Hampshire right now is making our concentrator photovoltaic array, which is comprised of triangular elements that lock together in a geodesic pattern to make what they call the dense receiver array. And I'll show a little more of that here in a second. So again, revisiting a little more detail on concentrator photovoltaic and what the advantages are of the sun cell. So this is a solar farm. It's like 100 megawatt. And they call it a farm because it actually is a farm. It used to be a farm, but now it's paneled over a solar panel. And this is about 250 acres, which is very extensive. Then you can say, well, I don't want to use 250 acres of these silicon panels. And so what I'll do, and of course you can't grow anything under here because the sun's being all collected by these dishes. But you have the same exact footprint if you go these concentrator photovoltaic. By concentrating the light, you're not actually using less land. You're still using the same amount of land. You have the same footprint. You're just concentrating the light so you have less coverage with the photovoltaic cells. So in the sun cell case, if you run very, very high concentration, which is actually working in the lab now, and I think our technology is going to push it to this massive concentration. You can even go up to 10,000 suns. So 10,000 suns is 10 million watts per square meter. I mean, that's like the biggest substation you could possibly imagine in a square meter, like cardboard thick. I mean, it's just insane amount of power density. And as you saw from that blast, we could create those kind of power densities. And it all gets down to how much heat you can remove. That's the whole limitation a concentrator will take. The PV cells themselves can handle it, but you have to take away that heat. So these microchannel plates, this cooling technology is where the frontier is to make even higher and higher concentration. But suffice it to say, you take something that's very small and replace something that's massive. It's like 75,000 times smaller. And that's a big increment. It's not like 20%. I mean, you make even a power plant, you can do 1 or 2% more efficiency or decrease the size. It's a very competitive internal combustion engine, incremental. But this is 75,000. It's a little bit more improvement. So then you got, this is it, the PV cooling, module cooling. This would be our dense receiver array. Again, I went through this ignition system. We're going to have an argon hydrogen gas that is in dome around this, and I'll explain that in a second. A silver and catalyst injection system, electromagnetic pump. This is an inductively coupled heater that starts it up. This is another invention that was really critical for this technology. Everything we're using is off the shelf, but it's absolutely incredibly the coolest stuff you can get. Like the inductively coupled heater, the metal organic continuous vapor deposition to make the concentrator PVs, the microchannel plates, the cooling system, the materials we're using, the supercapacitors from the storage industry, the inverters from solar, the concentrator photovoltaics from solar. Everything we're using is off the shelf, but it's incredibly amazing technology that had like $1 trillion investment, and just perfect timing that the power source is here at the same time. All this incredible technology is here, and the capability of mass manufacture. And that mass manufacture can come on very quickly. Within a year's time frame, we could put on enough what they call MOCVD to make pretty much the world's demand. What the manufacturers are saying is that it'll take about a year learn out to get and gear up to convert like LED manufacturing, light emitting diode technology to make these concentrator PVs with the same equipment, and that can come on very, very quickly. But with minuscule investment, like the investment you put in a few, like an oil field, would make enough capacity to supply all the concentrator PV that's required. So here's some other parts. We use hydrogen gas supply or argon. This is just inert gas, just to pressurize a chamber that goes around this. So when this gets super, super hot and builds up pressure inside, there's pressure from the outside that perfectly balance it. So it'll operate at about the pressure of a bike tire with a gas that won't even burn. It has hydrogen, but it's argon-hydrogen mixture at 3% hydrogen, won't even burn. It's called, they use it in glove boxes for welding, like doing inert gas welding. It's very, very popular and very safe. So more parts, there's a power supply for the inductively coupled heater, the EM pumps, there's ignition system, there's a startup battery, and then a water tank. But we may be able to even eliminate all this. Once we get up started, we may just run it just on its own, sustained. I'll show you this. The reaction can run sustained. So we may just start it up, and then we wouldn't even need this. We would use these systems to start it up in factory, and then all you would need is the black body radiator with the self-sustaining reaction and a system to supply it with hydrogen, which you can derive from the electrolysis of water. So there's more figures. Here's the radiator for cooling, and another view. We have a graphical user interface, so it's all push button and very user friendly. And this is what the outside housing looks like. So this would be basically very low temperature. It's got some cooling fins on it. This would be all enclosed. And the inside here is the the black body radiator, and it's pressurized to balance the pressure, so there's no net pressure across it. And then this is a pressure vessel, again, running at about the pressure of a bike tire with gas that can't even burn. It's a very safe system. It's a photovoltaic output, so we can go into commercial inverter and then go to AC loads, or we can go direct DC from the cell, like the 380 or 760 volt DC right into DC loads. So I suspect Edison's ultimately going to be the victor here. I think eventually everything will go DC. AC is good for phasing in different power sources, and it's good for transmission and phasing in those power sources. DC is actually more efficient, but then if you want to try and coordinate different power generators, it's better to use AC. But in this case, this is on-site power, and it makes more sense to just go DC, because pretty much everything is DC. You have to convert AC back into DC for most applications these days. You can use motors and cars. All of it can be DC power. So these are the parts, as I was saying, these are all commercial parts, and they take advantage of an enormous amount of work that others, so we're standing on the shoulders of a lot of ingenious engineers and diligent developers, but it's very advantageous for rapid proliferation to market. So the cost, this is, I'll go over that. So 250 kW, this is a one-of-a-kind. This is, if we order the parts and built the first one, comes out, the parts list adds up to $25,000. So it's about $100 a kilowatt. That will come down dramatically with volume production. But one of the key factors here is you look and you say, wow, almost all the cost is this. That's the photovoltaic converter. So right now it's priced at $50 a kilowatt. If we go to 10,000 suns, at more than 10 gig a year production, that comes down to, predicted by National Renewable Energy Lab, to $6 per kilowatt. It's amazingly cheap. I mean, so the message here is the capital equipment cost, unlike solar, we have a 20-year payback and you have change of ownership issues and things like that. This could pay for itself very quickly. Like, we're talking like a months, maybe even weeks once you get it to scale. So capital cost isn't really much of an issue. It's not a driver. And you don't have pollution issues. You don't have connection to the grid. You don't have regulatory issues. And the fuel is water vapor from the atmosphere. So again, the capital cost logistics are extremely favorable. But this is the main driver, and that's the thing to look for in terms of reduction cost, which we think will come down even below the extremely low value cost of $50 a kilowatt electric. So some of the prototypes, and looking at the timeline, so what we're doing currently is we're putting sensors and control systems on that device that I showed prior, the model. Well, not the model, that's the actual unit itself, and I'm going to show you it running. So, there's two levels of silver, because there's two molten metal injectors, and as they inject, those reservoirs empty out or fill up with the return flow. So the sensors would sense that and levelize it, control the electromagnetic pump speed so the levels would stay equal. And then the other thing is to keep a thermal profile that is above the melting point of silver and uniform through the reactor as we start it up and inject the molten silver, so the molten silver won't solidify at any given location in the cell. So those we have invented, and we've prototyped them on the bench, and they're I think very ingenious, very elegant solutions for the level controller. We have it all wireless, and we have state-of-the-art equipment running that. It's really very elegant technology for both those main sensor programs. So once that's on the cell, we can close it up, and we've got what we call the A prototype. That's the cell that'll run continuously closed without any visualization to control the levels of the reservoirs or the thermal profile of the cell. So I'm going to show it operating, and we're doing that by visualization and manual control of the levels, and as we start it up, the thermal profile is done visually. Once we get the sensors on, then the thing's completely automated. You just press it and it'll go through the whole startup steps up through ignition, and then ultimately turning the ignition off once it gets into the self-sustaining mode. So then that self-sustaining mode can be achieved with applying hydrogen and the catalyst. So that's the B prototype, and we're making these pretty much in parallel, the A and B. Then you get into a C, D, E. I'll just simplify it. We'll just call it A through E. And the C through E is more sophisticated variants of the photovoltaic converter that is puts out more power, more efficiency to go from a single layer to multi-layer to ultimately light recycling, and then more sophistication on the light source, and ultimately going up to higher power density on the light source in terms of emitter by going from 3,000 Kelvin to 3,500 Kelvin. So we're at 3,000 Kelvin, we're at 5 million watts per square meter. So a 6-inch dome will put out about 330 watts of light, and a 7-inch dome, which we're making, goes a little bit beyond 400,000 watts of light. So whatever your conversion efficiency is, that's how much net electric. So if we kick it up to 3,500 degrees Kelvin, it doubles that power density for the black body emitter. So rather than 5 million watts per square meter, it becomes 10 million watts per square meter. So the 6-inch dome would be 660,000 watts of light, and whatever your output is some conversion efficiency of that. So our first product is to make a PV converter with multi-junction light recycling that'll get us to 150,000 watts of light. Or excuse me, 150,000 watts of light from 660, somewhere between 330 and 660,000 watts of light. So it's going to be 150,000 watt DC electrical output, and then it can go into inverter and go AC from there. Inverters 90 plus conversion efficiency, so they don't really factor much into the capacity in terms of the product capacity that we're projecting. So I'm going to show you the reactor, and I just want to, let me turn this down a bit so you can hear me. Let's see, turn this down a bit. Okay, so I'm going to take questions, but I just want to explain a couple things here. So we have pumps, and right now we're just showing the pumps. There's a ridge here, so molten silver is being injected by the two pumps. Here's a reservoir that maybe be positive, one is negative, and the electromagnetic pump is pumping the molten metal here, and then it's running back to the reservoir. So you can see it's going to of course it's going to keep it a steady level. And there's the black body dome on top, but we have a hole in the top of it so we can look down through and see inside. So this is inside a vacuum chamber, and it's got a window that we can look inside the vacuum chamber and then ultimately inside the cell. And what we're going to do is we're going to turn up the pump current, so then the two beams intersect. Then we're going to gradually turn up the ignition power, and we're going to get it to ignite. And then we'll get a bright plasma from that. We'll run it a while, so the reaction's getting hotter, and it'll start vaporizing silver like you saw. Now it's just starting to ignite. And then we'll start vaporizing more and more silver, so we get more and more silver vapor pressure. We turn it off, and it'll sustain for a while. Then we turn the ignition back on, and it gets hotter yet, and then we turn it off, and it sustains. You can't see any difference with ignition power on or off. So ultimately, once it gets up to temperature, the point where the silver's at whatever its vapor pressure is, for the operating temperature of the reactor, it's high. It should be high enough that you don't even need the pumping. For example, at 3,000 Kelvin, the vapor pressure of silver will be 10 atmospheres. That should be sufficient that we won't even need the pumping. So we'll have no ignition, no pumping, no heater. So it should just run as long as we're providing hydrogen to the reaction. It's sealed with the molten silver, and you can see here now it's starting to ignite. And it's sealed with the source of catalyst. All we have to do is permeate hydrogen through the dome and have the hydrino vent out, and you've got a controlled reaction to make 3,000 degree Kelvin light to illuminate the PV panel, which is 5 million watts per square meter. As long as you control that temperature with the hydrogen, you've got a beautiful 24/7, 20-year power source for making electricity. It's very, very compact for everything from stationary through motive application. All right, so I'll take questions. You'll see ignition on, ignition off, and at the end you'll see ignition's off and still going, and it's self-sustaining at that point.
I understand where you get the hydrogen from, but where do you get the argon from?
Excuse me?
The argon. Where do you get the argon from? You have to...
Oh, argon? Yeah, my ears will clog from the plane. So the argon is in the bell jar. There's like a chamber that goes out around the PV converter and the black body radiator. So there's PV converter, and maybe even within microns to millimeters will be the PV panels. So you're getting direct illumination from black body right in the PV. And then I had the question, well, wait a minute. If that black body radiator is at 3,000, how are you keeping the PV from burning up? And then how are you going to get light going from the PV, which is like 80 degrees centigrade, back to the black body radiator? So so I'll just explain that, and then I'll get on to the argon, because it factors in the whole mechanism of how it works. So the black body radiation has that characteristic spectrum, and then it's absorbed by the PV and converted into electricity, and it might convert maybe 35% or so. And then as the light penetrates through the different layers of the photovoltaic, like the indium, maybe some combination of indium, aluminum, gallium arsenide, or at different layers. And it'll hit the back. And if you have gold's about 100% infrared reflector. So that'll reflect back to the PV dome. So it's really photons that are being transported. It's not really heating up and secondarily emitting the light as a black body radiator. It's just reflection of photons. So that's how you can have a cold radiator going back to something that's much hotter. So because the photons have a lot of energy. I mean, they're like if you have a photon, a red light, it's about 1 electron volt. So that's high energy. So photons can be absorbed by something very, very hot, based on a selective absorption mechanism, not being a heating mechanism, like where you have conduction or convection, where there's thermal motion. This is involving photon transport. So that's how that works. Then the black body radiator itself is going to get to very, very high temperatures, somewhere between 3,000 and 3,500 Kelvin, depending on how much black body power density and what spectrum we want it to emit. So the silver vapor pressure get to 10 atmospheres at 3,000 Kelvin. The tungsten dome can handle that. Or excuse me, the tungsten dome cannot handle that, but graphite can. As tungsten gets hot, it'll lose its structural integrity. But graphite has enough structural integrity that can withstand those kinds of pressures. Even more in compression. So we want to initially compress it with 10 atmospheres, and then as it heats up, it'll balance that pressure. So there's no net pressure across that black body radiator. So the argon is inert gas that we introduce into the outer bell jar and overpressure the black body radiator. So it's a one-time fill, and we'd fill it up to 10 atmospheres. Then we'd have a small percentage of hydrogen. Typically we're running argon 97%, hydrogen 3%. We may even run lower than that. Depends on what the permeability is at 3,000 degrees and how thick the graphite is, because the diffusion rate will determine what pressure of hydrogen we put in addition to argon. So it's a one-time fill.
Have you measured any beta radiation? Do you produce?
None at all. We have a spectrometer that can measure everything from less than an electron, 100,000 keV, all the way up, and there's absolutely nothing. No radiation at all. No. Yes.
Dr. Mills, how much energy do you get out of your hydrogen usage in terms of megajoules per kilogram?
If it goes, there's two reactions that we're interested in. One is we're using catalyst that makes the 1/4 hydrino state. So it's going from N is 1 to P is 4. So there's something called quantum numbers. When you're looking at states of hydrogen, they have to do with a formula in terms of what the distance the electron is away and what its energy level is, and some other characteristics about how many different multiplicit states it can have, multiplicity, in terms of when you put it in a magnetic field, like how many spectral lines you'll see and things like that. So there's the principal quantum numbers that are an integer, And then there's the hydrino states, which are also an integer, but the formula is reciprocal. It's like the inverse. So it'd be rather than n in a given formula, it's reciprocal p, where p is an integer. So we're going to 1,4 state. That'll release 204 electron volts per hydrogen atom. So to give you an idea, typical burning is 1 electron volt. So it's a lot more energy. And then if it goes down, it can go down to another state where you have that 1,4 state catalyzed atomic hydrogen, you go down to a much lower state, and potentially you can get a couple thousand times the energy of burning hydrogen. So it's probably some average of that is what we're looking to ultimately run this thing at. So, but very conservatively, 200 times the energy of burning hydrogen is a very conservative number in terms of energy balance. Yes, Peter?
In the sustainable modes, when it's self-operating,
Yes.
then these lower states are formed, or is it not yet?
We're looking into that now. We're looking into making that 1,4 state. In fact, we bought this very sensitive spectrometer you're asking about. We actually have an X-ray spectrometer that would look for the 3.4 keV line that astrophysicists have said they found a new line that doesn't belong to any known element that they're seeing from astrophysics. And that is this particular transition. Once you make the 1/4, then you get down to 1/17, and you will get a 3.48. I looked at their spectrum, and actually it has the same profile as our 1/4 transition. It's a continuum with a cutoff at the 3.48 keV. And so we're looking to make that, but you would have to contain the 1/4 state in order to make the 1/17 state. So we haven't seen that yet, but we're working on it. And there is no other X-ray. But we could detect even up to high energy X-ray, and there's nothing. So it's one of the things we work on, but remember, we're just running all open system until we can close it. And then we think we can get enough through the carbon that we'd be able to see it with a spectrometer. But we've got to contain the 1/4. Right now, it's very rapidly venting out, and without containment,
It's also going outside now.
it's not close.
heating up the carbon.
It is heating the carbon. Yeah, it is.
Not getting white hot. At this.
Oh yeah, it is. In fact, everything's molten here. So you got to figure it's at least 1,500 Kelvin, and based on the size, it's got to be at least 22,000 watts. Very minimum. If it's at 2,000, which is where we start vaporizing the silver at a very high rate, because the silver vapor pressure is 2263, then you're looking at over 100,000 watts from that black body surface. So it's making a lot of extra power. Just on inspection, you can go through a very quick calculation and confirm it's making a lot of extra power. Yes.
Interesting to know why you went for a black body emitter photovoltaic approach rather than a thermodynamically more efficient means of extracting energy out of the system like this from using photovoltaics. I'm just interested to know why you've gone that way.
Oh, if I use thermal, we use a steam turbine versus photovoltaic?
You use the example of the nuclear fusion guys, right? I mean, the concept of what they're doing is similar. They're just using nuclear reaction.
Oh, their nuclear reaction. In fact,
Not to my knowledge.
they don't use photovoltaics because they can't get a high enough power density. In fact, Massimo, we were up at Boston, and where you saw that the vaporization of the cell, the electrodes vaporized, that was on July 20th up in Columbia Technologies facility in Boston. We did that presentation, and we had Massimo, which is the concentrator photovoltaic manufacturer. They used to be Spire, and they have a world record for conversion efficiency by National Renewable Energy Lab. They're very good at concentrator PV. And Brad Siskovich got up there and gave a talk, and he said that he had spent a lot of his career, and at Spire and at Massimo, they'd spent decades working on thermal photovoltaic. Thermal photovoltaic is making something that's so hot it emits white light, and you convert that into electricity using photovoltaics. Now you're right, you could do that in a coal-fired plant or a gas plant or a nuclear plant or a fission, fusion, whatever kind of plant you meant, but the power density is vanishingly too small. And that's what he said. He spent decades. They could never find a power density source high enough to make thermal photovoltaic practical. And this is. It's the only thing there is out there to do it. Fission actually has a pretty low power density. Fission's like inside the cladding is only like 10 to 15 watts per cubic centimeter. It's not very high. This is on the order of 1,000,000 watts per cubic centimeter, to give you an idea.
I was going to ask you another question then. Is the black body emission, how stable? Do you know how stable that spectrum is?
Yes,
Because, my background on
right. We have to. That's going to be one of the engineering parameters that we have to control, is to keep the black body temperature constant.
Multi-junction solar cells are very sensitive.
Yes.
Spectrum. And the more junctions you put in, the more sensitive.
Exactly. Well, we could do other things too. We could do light splitting, like we could split the spectrum. We could use dichroic mirrors. There's other things we could do, and then there's another technique they're looking at. Rather than putting them in series, putting them in parallel. So you're stacking them, but each one would wouldn't have the same current. They wouldn't have the current go through each one of them, so they don't have to be current matched. So there's other strategies that are now in production that could.
If you want to get the 10,000 sums, then I'm sure a lot of those sorts of technologies would be required.
Yes.
Because you're generating a significant amount of current.
But there is a way of building there's a way of building triple junction cells without having them in series, so the current goes through all the cells, and thereby you eliminate that stability issue in terms of where the temperature and the stability. But we're at 3,000 Kelvin. We're going to be at fixed spectrum, so the spectrum is going to be locked in. So it's just a matter of maintaining a constant temperature, and how those cells respond as the black body temperature changes some amount. We have a fairly large thermal mass there too, so and the reaction is very, very fast and has a super high power density. So we think we can control it and keep the temperature constant enough that there won't be.
The converse is you can tune the solar cells to match the spectrum that you're producing to actually maximize the output.
Yes, and we'll design a cell to be congruent with a given operating temperature, and then we'll control that operating temperature. But because the reaction has such high power density and controllable by different parameters that we can control, we think we're going to be able to keep that temperature fairly constant. And there's other ways of design around the PV if it is an issue, though. Okay.
I'm not so much scientifically orientated than more maybe economically orientated. Is it possible to make it a little bit more less efficient and a little bit faster, to put it a little bit faster on the market?
Well, we're going. The first one we're putting out there is going to be like 30 kW. So we're going. That's a single junction.
That's the 2018.
No, we're going to go. Remember, there's the A prototype, which was just the closed system engineering without the sensors. And then B would be when we put the hydrogen chemistry in and get it into the self-sustaining mode. C is we add the first PV, and that'll be just single junction. Again, it's cheaper, move it along quicker. And then D would be when we have multi-junction and maybe some light recycling. C would be probably maybe even triple junction light recycling at a higher power from the light source. We are trying to move it as quickly as possible in terms of getting interim prototypes.
I expect the 30 kilowatt version would be ready to roll out.
Well, they're saying the PV maybe by February, March timeframe, and we need that in order to convert it. We have the sensors operational now. At least they're invented and are operating on the bench. They look like they're going to work very well. So we'll put those on over the next, I guess holidays coming up, but I'd say probably by the end of February we should have the closed cell going, and then March is when they're going to have the first, about end of February, March is when they have the first PV. I mean, nothing else fails. Everything in engineering, there's always some issue that comes up, but if everything goes according to plan, we're probably looking around March to put that first PV on there. Then of course we got to debug it, and we got to get the cooling system hooked up, and we got to make sure all the interconnects are working. They're complicated. There's microchannel plates. It's going to be operating extremely high intensity. It's going to be operating at least 1,000 suns. And then we got all the electrical interconnects, all the cooling interconnects, all the cooling systems. So there's quite a lot that's all got to get integrated into that.
What is the expected lifetime of the pumps, of the vacuum pump, of the water pump that is inside?
The water pump, we're going to probably have some kind of bolt-on tower that maybe like a snap-on. That's like a module, so that's a lifetime. Again, the entire equipment pays for itself like in weeks, and the cooling system is a very small component. Remember, the PV is almost the entire cost, so that might be just some stand-on bolt-on. I don't think it's going to be incidental in terms of the capital cost relative to the electricity value. So. But I think we overhaul our pumps every 6,000 hours or something like that. And
Once a year there's a maintenance.
yeah, and there's passive cooling systems you can go to. There's a lot of things you can do, but the pump's really not a big deal in terms of
No, I'm not asking
the capital cost.
The costs. I mean, just regarding the
the maintenance.
up and downtime and the maintenance. How often?
Oh yeah,
is it
most
something
pumps.
to
Yeah, most
exchange?
pumps. Like even we're only going to run the vacuum pump probably just for a fill, but I know that we overhaul them about once every 6,000 hours. So
In our business model, there's annual maintenance to support pumps and cleaning of the photovoltaic in case there's any carbon dust.
and that's something you can swap out. We have, as I was saying, we have these contract manufacturers that come out and depot repair centers. We could take the unit back, put another unit in. So there shouldn't be any downtime for the user. But it's all made modular. Like even the cooling is going to be modular. Someone would just come out, snap on one, and snap that one out, take it back, and it would probably just be more or less the seals and bearings that would need to be replaced. And I think manufacturers give us numbers like we routinely do ours about every 6,000 hours, but they said probably even twice that in terms of time that you'd have to do some kind of repairs for these pumps. Depends on how good a pump you get too.
It depends also on the environment where it's working. So.
Yeah, but you can control that.
It's only 3.
And that's going to be, we're going to use pool filtered water, so it's all going to be filtered. It's going to be very, very ideal conditions for pumping. Okay, any other questions? All right, good. Dominic's going to give the go-to-market next. Thank you very much.
So let me, maybe I'll just start because we can get through some of the statistics first about the market that we're addressing, which of course is relatively obvious. But if we start to think about the mission that we've got as a company over the next 18 to 24 months, it's quite prolific and quite daunting. So we've had to divide it up into a variety of different activities to manage it. So first of all, this small matter of creating a brand new primary energy source with a generator that uses this Hydrino process to deliver this safe, economic and clean power is what we've talked about. And that's obviously the primary mission of the company and has been the primary mission of the company since its inception, as Dr. Mills took you through in the time frame. Second part of our mission, which is the bit that I have responsibility for, is the launching of that technology to market. And when you look at the way that we're phasing that, we're starting with the stationary market, and there are reasons why, and I'll go into those here in a second. We're going to do that through a direct lease model. We're going to focus on operating Brilliant Light Power subsidiaries in at least certainly through our initial investigation, 30 of the world's 196 countries, or 195 if you're Chinese, because they don't accept Taiwan. But that is really where we're going to be operating. So literally, Brilliant Light Power Limited here in the UK will be operating as a leasing co, and we will have a setup that allows that to happen. Our whole model and the focus of our model is about disrupting legacy energy technology. So we aren't there to support grid generation. We get a lot of time, people coming to us and saying, are you going to put grid generators in? No. We're focused very wholeheartedly on moving to a distributed model. And that's key, because with the exception of microgrid technology, which of course we will want to utilize to service single-family homes that won't be needing 150 kilowatts of power, we've got to be very, very focused on our mission if we're going to be successful. And then finally, and indirectly, we are obviously going to solve a lot of the world's problems. Maybe start a few problems as well. We're conscious of those as to how we introduce the technology. But it's very important that we use this technology to solve world energy shortages. Certainly, when we talk to some of the groups that are here in this room that represent commercial entities, they actually say, well, it's great that you can supply me this cheap energy in the UK, but what about India? That's my big problem. I need to get out there first and support my services over there because I don't have another way of getting power, let alone clean, cheap and renewable power out to deliver those services. So that's very, very important. And as a byproduct, we're going to change the geopolitical landscape as we know today. So when we look at our market, it's one of those very rare opportunities you can sit down and really have to analyze in the trillions the market opportunity that you're looking at. So this $8 trillion of fossil fuels that are consumed and burned globally today, and the energy that they generate, about $1 trillion actually just to maintain that infrastructure, which is a phenomenal amount to maintain a system on a global scale to be able to deliver energy to the amount of people that consume it today. Energy clearly is not only in demand, but it's also in rapid growth. The number of applications that energy can, the energy is required to support is, of course, pretty much everything. And so we've got to be very, very focused on the areas that we start to make sure that we have the best and most economic impact. And then, of course, there's the environmental part to that. So whilst there have been massive advances in renewable technologies, we were in Washington, D.C. last week, on Tuesday, talking to a number of the pioneers of that, to the people that had worked within, in fact, the Clinton administration that had actually started a lot of that renewable focus. But they admit, and these are the guys that architected it, that the current state of renewable isn't going to work. And of course, with the new administration coming in, actually, and the change in focus of the US political landscape, really the only way that they see being able to solve what they consider as a climate crisis is to have an economic solution to it, which is what we offer and we provide. So that's the difference here. It's not about clean, renewable, save the planet. It's actually, let's do that economically, because we've got a technology that will allow us to do that and supply it at a much lower cost. Electricity is obviously the first market for us to start with. As I talked to you about before, stationary markets are easier for us to address, largely because of the structure of the unit and the way we can deliver it. It's about $3.5 trillion market. On average, about 12 cents a kilowatt hour on a global basis. Of course, that varies tremendously, dependent on where you are in the world, and certainly we're having conversations in the Caribbean and Hawaii where that number is 3 or 4 times, even more. In fact, I was just speaking to Jeremy Hux here earlier about California, a residential rate of 32 cents per kilowatt hour, which is pretty significant. And of course, Europe varies, as we all know, whether you're from Germany or from the Netherlands or from Scandinavian countries, very, very differently, dependent on the sources that are available. There's also, when we talk about that market, actually because of the economics of it, we see about $1.5 trillion of that market being addressable. Now, what that means is we're taking that market and we're devaluing it. So as it stands today, because we're providing power at a lower cost, we're devaluing the market. We understand that. But because of this great increase in demand, and of course, not only is there an increase in demand with the existing power sources, but what could you do if I gave you a clean, cheap, renewable source? We expect that to accelerate materially. And that's really where we're going to revalue the market and rebaseline it at a different level. We talked about the global electricity market being the obvious fit. It's about 42% of the value, about 38% of the total energy use. But of course, there are non-electric markets as well, and I'll talk quickly about the motive markets as we get to it. But again, as we look into it, that's great. We see the existing markets as very good, but what else can we do? What else can we electrify? What else can we deliver power to? What other processes could we do to create new businesses and drive new industries as a result of this technology? Quickly, just looking at motive, it's a second phase focus for us. After we've moved through the stationary markets, we begin to look at motive markets. Again, 27% of energy is consumed by the transport industry. What's interesting is 700 million passenger cars only operate about 5% of the time. Something to consider is, of course, once the sun sail's on, it's on. What do you do with power, a sun cell powered vehicle, in the time that it's not actually moving? At the moment, you're going to dump the power, but there could be other applications that those vehicles could be applied to that we haven't considered. The other thing that's really interesting about the motive market is it's very, very quick to penetrate. 68 million cars are produced every year, so about 10% of that market is renewing on a consistent basis. So actually, within 10 years of introducing sun cells into cars, we could, in fact, have sun cell powered the motive market. It would be the predominant internal combustion, goodbye, sun cell now driving that market, which is why it's so exciting. But I do think, and we've sort of alluded to it in this presentation before, whilst that is, and the existing markets are really good, the real opportunity for us, when you look at this diagram and how much of the world is electrified and what power is currently being consumed, is what we can do with technology that the sun cell is going to be able to deliver on a global basis once it's in existence. So, I'm just going to touch on our go-to-market model. As I said in DC last week, I don't know if any of you watched that video, but the good news is when we developed this, we've stuck with it. It hasn't changed. When you look at the applications, we've got the stationary and the motive markets as we talked about. We're going to directly lease, as we discussed, and we're going to operate through distributors in markets where we will not have Brilliant Light Power leasing countries, so we'll have proxy organizations and partners that we'll be working with. And similarly, in the motive markets, we will lease where that's possible, but we will also work with development partners, motive specialists, to be able to take that sun cell into the motive, whether that be automotive, commercial, or even marine environment to get that done. Our first stage is industrial and commercial consumption, largely because we're making a 150 kilowatt unit. We are throwing in to that, of course, multi-tenant residential, where we can see apartment buildings that would be able to use that have enough density or power density to be able to support it. And then The second stage is residential and commercial motive. With residential, there are a number of ways we're going to address it. We have considered a 10 kilowatt unit, so as a standalone unit that would be able to be addressed, and that continues to be a consideration of the company. Of course, it's not our primary focus today. With commercial motive, again, we have now MOUs with organizations that build those commercial vehicles that we have already and are working on to develop those applications. So it's not something we're thinking about building a truck, just to be clear. We're very focused on the power source that's going to be in that truck. And then there's a third stage. We're looking at consumer automotive, again, working with development partners, and finally, marine. Okay? There is one other group that is a focus of ours right now, and that's, of course, all of the other applications that the SunCell can solve. We have a program that we've built for development partners to come and work with us as an organization and build projects that are focused in areas that we're just not looking at. I've given you 3 examples here of obviously space applications, military and heavy industry, but there are many more. You can look at agriculture, you could look at ammonia production. There are many others that we see that we'll be working with and conversations that we're entertaining. The other thing that the development partners are obviously interested in isn't just the power source, but also the other commercial properties that come as a result of the reaction and the science that we've supported. So, as Dr. Mills talked about, tremendous amounts of heat. We also have tremendous amounts of light from the plasma, as you've seen from the demonstrations. And of course, the dihydrogen gas, which we talked about as lighter than air, is actually a helium substitute. We can make that very, very cheaply, and when you consider the cost of helium today, it's actually a very compelling business model in its own right. So this is the simple launch pricing model that we talked about last week in DC, and just when you look at the working with commercial organizations, very simply, we're charging $90 a day for a SunCell. So if you use that SunCell, that 150 kilowatt SunCell, and I can send you this presentation as well if you need it to take some notes. Please I'll make sure you got my card before we go. But very simply, if you use that 100% of the time, you're going to be getting 2.5 cents per kilowatt hour. If you use it 50% of the time, which most, I guess, office buildings and commercial buildings are going to be using of that total capacity, then you're going to be getting about 5 cents. So we're incentivizing you to use as much of the power as is available. And in fact, we want you to buy more, and we'll make it readily available for you. But it's just very simple. As an installation fee, and I'm talking about markets, as in what I would consider developed markets, we calculate the installation fee, one-time installation fee of $2,000 per SunCell. Now, of course, that will vary if we're installing thousands of them, all in the same location. And with some of the customers we're talking to, that will be the case. Brilliant Light is responsible in this model for, obviously, the installation, certification, the insurance, the maintenance, as we talked about, and obviously the customer management and billing through the subsidiary leasing companies that we discussed. But all of the installation and maintenance within the business plan is outsourced. So again, another great opportunity for other businesses to work within our ecosystem to be able to support that. Okay. So this is the distributor model. Now, I've said this before. we are not going to sign distributors in markets that are ones that we want to serve. So those 30 countries that we talked about geographically, we will be looking to serve those with Brilliant Light Power subsidiaries. However, in some of the markets that are more difficult to address without a partner, that's where we'll be using the distributor model. That would include certainly we're looking at the moment at India, potentially China or Russia or some of the BRIC countries that we're talking about, and obviously parts of Africa as well, where that is. It would be difficult for us to operate without that partner, and other companies already have the workforce on the ground to be able to support that with the electrical engineering skills to be able to deliver the service that we want. In that case, the distributor is responsible for the installation, the certification, insurance, the maintenance, and obviously the customer billing. What's important to understand here is that we are charging the distributor a minimum of $45 a day. It's actually a 50-50 revenue split. There is a pricing floor. They cannot undercut us. Contractually, the distributor will be forced into providing a minimum pricing floor of $90 a day. That may vary on a country-by-country basis. We're charging a license fee of $5,000 per megawatt electric, which is really our way, because we don't want to impair the distribution model. It's just making sure that they're serious. So the distributors that we're signing up today, if you think about that, are paying those fees to be able to operate in this model. And equally, on order, they are contributing to the production cost, even though we own the units of the sun cells that support the delivery of the power in their region. Okay? So the only thing in this model that we look to support, of course, is we're shipping the sun cells to the distributor, and obviously we will warrant the fact that the sun cells themselves work, which are backed off by manufacturing guarantees. What's really interesting, when you look at our business and our business model, we pre-launch, which is Q1 of 2018, working with a model where we are pre-selling capacity, so we're working with groups to actually commit to using the power. We have a target of about 10 gigawatts. And if you take that model and assume that 50% of it is directly leased and 50% is through a distribution model, which is nearly 70,000 sun cells that will be deployed over the first 24 months. We have about 25 million in distributor licensing fees. There's an opportunity for, and this is just in our, not the distributors, but in our half of that where we're using a direct leasing model, of about 67 million for a third parties to come in and work with us on the installation and maintenance. There's about 375 million in capital contribution that we're going to be using to support the production of those sun cells. Once fully deployed in this model using the numbers I talked about, actually Brilliant Light Power is a $1.7 billion company, recurring revenue. So tackling this world market is a very profitable concern, and the company will grow very, very rapidly, even though we're reducing the unit price of power as it exists today.